Hi guys, this is lesson 7.6 called Growth and Decay. We've already talked about this a little bit, but we're going to flesh this out a little bit and make our equations just a little more practical. So the first key concept today is an equation for exponential growth. Taking the time to write these things as I talk, because I know that you're writing them as well as you take notes. So we have y equals a times 1 plus r to the t. This is very much like our y equals a b to the x. We're just putting in a little more detail. In this case, y is the same as y, a is the same as a, it's still the starting amount, and then b is just a little different here. We're going to describe b as 1 plus a rate. So the 1, remember I told you the exponential graphs would not be growth or decay. If we only had a 1, everything would stay the same. So the 1 actually represents that staying the same. And then we're going to have plus r, which adds a growth rate. So I'll show you some examples in just a minute. And then t is going to be the same thing as x. And usually, I think I already mentioned, but t or x is often time. So we have a rate happening to an initial amount. Here's our initial amount. And over time, it's going to generate a final amount, or y. So let's have an example here. It says, the prize for a radio station contest begins with a $100 gift card. Begins with a $100 gift card. Sounds like an A to me. Once a day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. Now, if I were to convert 2.5% into a decimal, I'd have 0.025. And if I put 0.025 in for my B number, that would be a fraction or a decimal, which would cause decay. So I'm actually going to end up with 1.025 in order to show that growth. So let me just fill in these details. We had y equals a $100 gift card, so that's our A. And then we had 1 plus the rate, and the rate was 2.5%, and 2.5% is the same as 0.025. So we have 1 plus 0.025, and we're going to do that to the t, or time. And then that's my equation that will tell me how much the prize is on any given day with no winners. So how much would the gift card be worth if no one wins after 10 days? So what we would do is y equals 100. We can combine the 1 and the 0.025. And then we would plug in, say, a 10 here and need to do that math. If you're doing that in a calculator, be a little careful about order of operations. Lots of times the calculators are actually pretty smart, but you don't want it to mess you up. I often just go ahead and I actually think my battery is completely dead right now, so I can't even plug that in, but I will do 1.025 to the 10th power, hit equal, and then times 100. And then what you get is 128.01. Y equals 128.01. And that's how many dollars the prize is worth now. Okay, so let's go to another practical example, and it is called compound interest. So this is another key concept. And I think I told you before that one of the most exciting examples of exponential growth is financial investments. So compound interest is one of these. Up till now, you've probably just solved for simple interest, but compound interest is actually more real life. What happens is this A is going to be our end amount of money. We start with something called principal, P for principal. That's just the A. It's the same thing as the A in our exponential growth equation. It's an amount of money that we're going to start with. And then what we're going to do is we're going to have 1 plus a rate. I'll show you what this is going to be in just a minute. And then we are going to have time that goes by. So compound interest means that I get interest on my interest. In fact, it's like saying, okay, I'm going to invest my money for maybe a period of time, and normally I would get interest maybe every year, but I want my interest a little sooner than that. And so maybe after 1 month, I want to get 1/12 of my interest for that year, and they will pay me that 1/12 of the interest, and that goes in with my principal. And so the second month, I not only get the second 1/12 of my interest, but they calculate interest on the interest I've already earned. So it kind of piles up like this. And as I get interest, a fraction of my interest added onto me, I am going to actually be earning even more interest on that. So here's an example. It says Maria's parents invested $14,000 at 6% per year compounded monthly. How much money will there be in the account after 10 years? So it doesn't mean that they're going to get 6% interest every month, but they are going to get a 1/12 of the year's interest every month. So here's how this works. They have an amount that's going to be, that's the Y. A is the same thing as Y. And that's going to be the amount that they have at any given time total. The principal that they invested was $14,000, and it was at 6% interest. We're going to do 1 plus, and then 6% is the same as 0.06. And then what this is over N is the number of compounding periods. So we're actually going to compound monthly. So we're going to divide that 6% by 12 actual payments of interest. And then that is going to be we decided 10 years is our time. But remember that we're getting 12 payments every year. So we're going to multiply by 12 there. So N in this case is the number of payments that you get your yearly interest in. So we have interest that's getting paid before the end of the year, and it becomes interest on interest. Watch out when you're solving these that you apply. If we do 0.06 over 12, we get 0.005 to add on to our 1. And we're going to do this to the 120th power. So we need to do 1.005 to the 120th power, hit enter, and then multiply that times our $14,000. And so what we find out is that the amount we have at the end of that is going to be $25,471.55 that we have rounded it at in 10 years. So our investment has grown. So our graph is going to look like, starting at 14,000, it kind of goes along a gaining interest, but then the interest starts to earn interest, and it starts to climb pretty fast. This amount is going to keep doing this, and the longer it's left to earn at 6%, the better it's going to do. All right, so compound interest is a great example of exponential growth. Let's talk about exponential decay. So this is another key concept. We're going to talk about exponential decay. So just like the exponential growth, we're going to have y equals A is our starting amount times our 1. That's our status quo. That means nothing changes. But this time we're going to subtract a rate to a time. So x is the same thing as t, y is just y, a is the starting amount, and 1 minus r is b for this. So here's an example. It says a fully inflated child's raft for a pool is losing 6.6% of its air every day. The raft originally contained 4,500 cubic inches of air. So let's write this equation. We have y, that's the amount of air in our raft, equals the original amount of air was 4,500 cubic inches of air. And then we had 1 minus the rate it's losing is 6.6%. And we have to move that decimal to be 0.066. So 0.066 is our rate, and that goes to a time. Then we can simplify this equation a little bit. Y equals 4,500 times 0.934. So notice that that number is less than 1, so it is exponential decay, and our air is going down. And so that this equation will represent how much air is left in the raft after a certain number of days. T is in days. So if I wanted to know how much air was left in the raft after 7 days, I would put my 7 in for x, and then use my calculator. 0.934 to the 7th power equals, and then times 4,500, and I would get y is about equal to 2790, and that is how much air is, how many cubic inches of air are left in the raft. All right, so things to remember from this lesson. Exponential decay. This is an expanded concept from the one that we did in lesson 7.5. Y equals a times 1 minus the rate to the time. And this concept just helps us to fill in the information that we have from a word problem a little bit better so we can create an equation. Let's go back to the key concept of exponential growth. We have y equals a times 1 plus the rate to the time. And then we also dug in a little deeper to the key concept about compound interest, which is a great example of exponential growth. And the equation for that looks just like this. P is our principal that we invest, 1 plus our rate divided by the number of payments we're going to get that rate given to us in, because we're going to ask for that interest to be paid to us a little early in fractional amounts, but we're also going to have that money, and so when we calculate the next interest payment that's owed to us, it will include more money, and so we're going to get interest paid on interest. And this creates a nice situation where our money is growing at an exponential rate. So go ahead and try your problems in Alex and let me know what questions come up.